This is a talk on spin-gravity coupling via pairs of entangled electrons in a gravitational wave. My name is Ray Chiao. I'm a professor emeritus at the University of California at Merced, and this is a talk at the APEC conference on August 5th, 2023. Next slide, please. There has been a recent search for spin-gravity coupling by the authors are S.B. Zhang et al., and the title of the paper is Search for Spin-Dependent Gravitational Interactions at Earth Range, and it was published in PhysRev Letters last May. The authors searched for a spin-gravity interaction Hamiltonian of the form where x is some unknown constant that mediates the coupling between the spin s and the gravitational g field of the Earth. They found that the magnitude of this spin gravity interaction Hamiltonian is less than 5 times, it's missing here, 10 to the minus 22 electron volts in isotopes of xenon. However, they did not explore the possibility of a huge enhancement of the spin-gravity interaction that arises from the entangled states of electron pairs in ferromagnetic materials. Next slide, please. Let us begin with a classical spherical model of the electron, which consists of a spinning ball, indicated in green here, of charge E, mass m sub E, that's missing mass m sub E, that's the electron mass, and a spin s, which is this red arrow pointing upwards. Now, the spin implies that it is a gyroscope because spinning objects are gyroscopes that can be used for inertial guidance. For example, a gyroscope can point towards the North Star Polaris and can be used for inertial guidance. Here we show this green spinning ball, which has an equatorial velocity v, which carries an electrical current with it because the ball is charged, and therefore there is a generation of a magnetic field line indicated here in purple that loops from the South Pole over to the North Pole, and therefore there is a magnetic moment mu that's generated by the spin s. Next slide, please. Oh no. Hey, Tim.
Yeah,
problem.
So let me take a look. Okay, you have animations there. Okay. So the animations are not playing in this, and I am not sure how to get those to play. We may be a little bit stuck. Is that something that you could just describe for us, do you think?
It's going to be hard. I need the equations. And
yes.
It's missing from this.
Okay. Well, let me see. You know what? Let me bring in Jeremy. Let me bring in Jeremy really quick because Jeremy's here. Jeremy, how do you think that we might be able to fix this?
What's going on? I'm trying to work.
Yeah, he has animated equations. Actually, you know what? I know what we can do. Hang on. I bet that if I save this as a PDF.
Let's see here.
Okay.
Streaming on. I wanted to broadcast this in the live. We're doing the live feed of the superconductors baking in this oven right behind me. our LK99. So
Okay.
I was trying to get that set up, but let me think. If
You know
it's
what?
in his
L- l-
equation, if you could do like a screen capture of the screen rather than I don't know if there's a second way to do it through another party like OBS or something. I don't know what you're running, but
Yeah. Well, actually, let me try this. I'm going to remove that. I will add that.
Now,
There we go.
yes, now it works. Yes,
Okay.
great.
Quick
Okay,
fix. Quick fix. Okay, Jeremy, thank you for your help, sir. Let me remove you back out. Okay, and let me see. We're on slide 4, right? Right.
right. Okay,
Wonderful. My apologies for the difficulties. I think we should be good now. Okay.
okay. Can I get back now? This is a slide describing the gyromagnetic ratio of the electron, which is denoted by the Greek letter gamma, and it's defined as the ratio of the magnetic moment mu divided by the spin s of the electron. And it works out that this gyromagnetic ratio is approximately the charge of the electron E divided by the mass m sub E of the electron. And experiments have shown that this gyromagnetic ratio is minus 1.76 times 10 to the 11th coulombs per kilogram. This is a huge quantity because the mass of the electron m sub E that appears in the denominator of the gyromagnetic ratio gamma is a very tiny quantity. And it is important to note that the gyromagnetic ratio gamma and not Newton's constant G, that is the gravitational constant G, nor Einstein's kappa, that is the coupling constant that couples the Einstein curvature tensor to the stress energy tensor. None of the capital G or kappa couples electron spin to gravity and to gravitational waves. Since the range of the entangled state is very large, the scattering cross-section for gravitational waves can also be very large. Okay, next slide, please, Tim. Next slide, Tim, please. Oh, yes, here. This is a slide on Einstein's field equations, which can be written as G sub mu nu is equal to kappa times T sub mu nu, where G sub mu nu is Einstein's curvature tensor and kappa is Einstein's tiny coupling constant. It's given by 4 pi Newton's constant, capital G, divided by c, the speed of light, to the 4th power. And since the speed of light is a huge quantity, the 4th power of it is even much larger quantity. And therefore, it turns out kappa is 2 times 10 to the minus 43 Newtons inverse. The inverse Newtons are the dimensions of kappa. And it is a very, very small quantity. And also the T mu nu on the right side of Einstein's field equation is the stress energy tensor. But note that the stress energy tensor T mu nu doesn't include the spin 1/2 h bar, where h bar is Planck's constant divided by 2 pi of the electron. So the spin of the electron is missing in Einstein's field equation. Next slide, please. Now we turn to the quantum mechanics of this problem. Consider entangled states of 2 electrons in a magnet. The total wave function for 2 identical electrons is described by psi subtotal of 4 variables. The first is R1, which is the location of electron 1, R2, which is the location of electron 2, And then tau1 is the spin variable of the first electron, and tau2 is the spin variable of the second electron. This total wave function can always be factorized into a spatial part and a spinor part. The spatial part is denoted by capital Phi of R1 and R2, the two positions of the two electrons, times chi, a spinor wave function of tau1 and tau2, which are the spin variables of electrons 1 and 2. Now, there is an important symmetry in this problem. The electrons are fermions, and they must obey what is called fermionic exchange symmetry. That is to say, the total wave function must be totally antisymmetric under the interchange of the two electrons 1 and 2. Thus, if it is the case that the spinor wave function chi is an even function of tau1 and tau2, then that happens when the electrons are in a spin triplet state. Then it follows that the spatial wave function capital Phi must be an odd function under interchange. An example of this is when the spatial wave function is a superposition state of two product states of single electron states, which are denoted by capital Phi sub p minus p of the two position variables. And this is an entangled state. An entangled state is defined as a superposition of the product of two single particle states. And it is important to note that the superposition occurs here with a minus sign in the middle. So that means that if we were to set R1 equal to R2, that is to say, if the electron 1 happens to coincide in location exactly with the position R2 of the second electron, then obviously the wave function vanishes due to this minus sign. And this is the Pauli exclusion principle. Okay, next slide, please. It turns out that experiments show violations of Bell's inequalities by entangled states. Now, the equivalence principle of general relativity is a local principle which relies on the locality of all physical systems. That is to say, their spatial separability. Entangled states, on the other hand, imply quantum violations of spatial separability. For example, the entangled state in a two-electron system in a magnet that was shown in the previous slide. These entangled states cannot be factorized, and so they are not spatially separable. Einstein, Podolsky, and Rosen showed that entangled states are non-local. That is to say, they are spatially non-separable. For example, a measurement of the momentum of one electron instantly leads to the measurement of the opposite momentum of the other electron in the example shown in the previous slide. However, experiments contradict Bell's inequalities that follow from spatial separability assumptions, and thus the locality of the equivalence principle is violated. What consequences does this lead to? In the next slide, please, Tim. We summarize what we have learned so far, that two electrons in a magnet are in an entangled state which obeys fermionic exchange symmetry. The two green spheres here represent two electrons with spins pointing upwards, So they are in a spin triplet state. And therefore, under exchange symmetry, their spatial wave functions must be odd, which means that if one were to measure the momentum of the first electron on the left and it were to point towards the left, then instantly at the right electron must have a momentum that's pointing to the right, and this follows from the conservation of momentum, in which the total momentum of the two electron system must be always conserved under all circumstances. Likewise, the two electrons, if one were to measure the momentum of the electron and it was pointing to the right, then instantly at a distance, the right electron would exhibit a momentum that's pointing to the left, again, in order to conserve momentum. So there are correlated outcomes of measurements in an entangled state. That leads to an interesting interaction with gravitational waves, as shown in the next slide. Next slide, please. So consider two electrons indicated in green here with their two spins indicated in red. And I am going to try to convince you that the spins of two entangled electrons in a passing gravitational wave tilt in compass needle librational motions or tilting motions that are indicated here. So imagine that a gravitational wave comes in from the left with a wave vector k subgravitational at t equals 0, supposing that the gravitational wave has gravitational fields G, which is pointing downwards on at the plane z equals 0 and pointing upwards minus g at the same plane. This indicates that the gravitational wave is squeezing space as the tips of these two arrows are pointing towards the z-axis. Likewise, half a wavelength later at the plane z equals lambda over 2, the gravitational fields G and minus G reverse in sign such that the gravitational fields are going away from the z-axis, and this shows that the gravitational fields of the gravitational wave are stretching space away from the z-axis at the plane z equals lambda over 2. This means that there will be tilting motions of the spin vectors indicated in red, and this is shown in the next slide. Next slide, please, Tim. So we answer here, why do the spins of two entangled electrons passing over the gravitational wave tilt towards each other? And we must start from the fact that spins of the electron S are gyroscopes, and they point towards freely floating dust particles indicated by the blue dots here, A, blue, and B, blue, C, blue, D, blue, such that the tips of the spin vectors point towards these blue dots, both at the tail and at the front of these spin vectors. The spin vectors are following the motions of these freely floating dust particles. And therefore, the squeezing of space produced by the gravitational fields G and minus G of the incoming gravitational waves causes the dust particles to move towards each other at z equals 0 and away from each other at z equals lambda over 2, half a wavelength away, and therefore there results a tilting motion of the spin vectors indicated in red. But remember, the spin vectors are coupled to the magnetic moment of the electrons. And if the spins are tilting, then so must the magnetic moments be tilting. And the motion of the magnetic moments leads to the emission of gravitational electromagnetic waves because of the magnetic moment changing in time. Therefore, the gravitational wave is transduced, that is, it's converted as it passes over the two electron system. It is going to produce electromagnetic waves indicated by the wave vector k sub electromagnetic, which goes out to the right. Now, imagine that we were to take a movie of this process of transduction from gravitational waves coming in from the left and leaving as electromagnetic waves going to the right. Then, by time reversal symmetry, the electromagnetic waves, which are coming in from the right in time reversal, as they pass over the two electron system, they produce tilting motions of the spins in such a way that it generates a gravitational wave. So it goes both ways. A gravitational wave can be converted into an electromagnetic wave, and by reciprocity, the electromagnetic wave can be back converted into an into a gravitational wave. It goes both ways. Okay, so next slide, please. Now, here is a possible practical implementation of these ideas. Consider putting two Ig spheres into a gravitational wave. The Ig spheres are indicated by these yellow spheres, one on the left side and one on the right side. And let a gravitational wave here shown face on, not side view, but a face on view, which can be described by these blue hyperbolas as force fields of the gravitational wave. And now consider the motion of two electrons indicated by the red dots in the presence of these force fields. The force fields along the z-axis are denoted by G, that is the gravitational field of the gravitational wave is pointing on the left to the, is an arrow which is pointing to the right on the left side of the diagram, and the gravitational field on the right side is pointing towards the left. Thus, there is a squeezing of space in between the tips of the two gravitational field vectors. The squeezing of space produces motion of the spin of the two electrons indicated in red, such that the spin vectors indicated by the red dots with the red circle around them, the spin vectors will tilt towards each other, indicated by the green arrows with velocities v and minus v, respectively. So the two spin vectors tilt towards each other, and therefore, because the spins carry magnetic fields with them, because there's a magnetic moment that's moving, the motion of the magnetic field produces electric fields, and it works out that the motional electric fields is pointing upwards on the left side and pointing downwards on the right side. And so this is how a gravitational wave is converted into an electromagnetic wave. It's via emotional EMF that is generated by the motions of the spin vectors of the two electrons. Okay, in the next slide, we show a photo of a Higgs sphere. This is a Higgs sphere whose diameter is approximately 300 microns, and it was produced in a machine that is used for polishing gems that tumbles a single crystal of Ig. That Ig, by the way, stands for yttrium iron garnet, which is a ferrite material, and produces this black sphere which you see. And this black ball that you see is a magnetized ball. It has a permanent magnetic field from it, just like in a magnet. And this magnetization is equal to the magnetic moment of all these electrons in the ball per unit volume. And so, because there are a large number of electrons in this ball, the magnetization of this ball could be huge. And in practice, there are fields of the Higgs spheres that are produced on the order of 1,000 Gauss, or about a tenth of a Tesla. Okay, next slide, please. The spins in the ball undergo spin precession in a magnetic field and leads to magnetic spin resonance. Here is a sketch of how this spin precession proceeds. In the red here is indicated the spin vector S, and the tip of this vector is orbiting in a circular orbit around the z-axis, the vertical axis, in a blue circle here. The blue circle is the orbit of the tip of this spin vector when there is a permanent magnetic field, B naught, or DC magnetic field, or remnant magnetic field due to the magnetization of the Higgs sphere. So now let's apply, in addition, an RF, or radio frequency magnetic field, indicated by the radio magnetic field B sub RF that points towards the tip of the red vector S. And if we tune the RF frequency so that it is in resonance with the motion of the spin vector, that is to say, if the tip of the red vector coincides at all times with the tip of the purple vector of the RF magnetic field, then we have what is called spin resonance, in which there is a transfer of energy from the RF, or from the radio frequency field, to the spins, and vice versa. There could be a back transfer from the spins back into the RF field. So there's both emission and absorption of RF radiation, and that is possible when you have magnetic spin resonance. The next slide, please. Now we describe the power emitted or absorbed in electron spin resonance. This, this can be described by an equation which equates the torque, which is given by mu cross. This diamond symbol should be a cross symbol. Sorry about the font mistake. It's mu cross B is the torque, and that is equal to the time rate of change of the spin vector S with respect to time. And so we get a differential equation, ds dt is equal to gamma S, that's the magnetic moment, mu, cross, that diamond shape is again the cross product of S cross B. And this can be solved, this equation of motion can be solved, and we can calculate the power by taking the dot product of the torque with the instantaneous angular velocity of the spin vector, and taking a time average of it gives us the power. And it turns out the answer to this calculation is that the power emitted per electron is given by gamma squared, the square of the gyromagnetic ratio, times the magnitude of the spin vector S, times the magnitude of the DC magnetic field V naught, times the magnetic field B sub RF of the radio frequency magnetic field. So let's put in now some numbers. Since gamma is a very large number, gamma is minus 1.76 times 10 to the 11 coulombs per kilogram. Gamma squared is an even larger, huger number, and this allows us to do the experiment. Or if we put in now the remnant magnetic field of a typical Ig sphere, which is around B naught is around a tenth of a Tesla, or about 1,000 Gauss, and we put in B sub RF for the radio frequency magnetic field to be 6 microtesla, which is for a 1 watt of RF power applied to the system at microwave frequencies at 10 gigahertz. Then the time average power emitted per electron works out to be around 1 attowatt, or 10 to the minus 18 watts, but this is per electron, and there's a lot of electrons inside the Ig sphere. So in the next slide, we calculate, next slide please, we calculate the power emitted in gravitational waves by 2 Ig spheres. And the number of electrons in a millimole of a millimole Ig sphere is 10 to the minus 3 of Avogadro's number, which is around 6 times 10 to the 20th electrons. It's a huge number. And therefore, the total power in gravitational waves emitted or absorbed by electrons in 2 Ig spheres is around 600 watts divided by the Q of the spin resonance. QRF is the magnetic spin resonance quality factor. And if the quality factor, as experiments show, can be around 600, then we get that the power emitted in gravitational waves by the 2 Ig spheres can be on the order of watts. It's a huge number. And the reason for this is because Avogadro's number is a huge number. Okay, and now we can look at it. The next slide, please, Tim. Here is a possible experiment, and we call it a Hertz-like experiment for gravitational waves. Supposing we have a transmitter and a receiver placed in 2 rounded Faraday cages. The left one contains inside it 2 antennas indicated here in orange, and they generate an electromagnetic wave which irradiates a pair of levitated Ig spheres. These spheres can be levitated, for example, above superconductors at millikelvin temperatures, above a RF stub cavity, which makes it have a high Q, and the temperature is low, so that the quality factors here of the spin resonance can be quite high. And so the incident electromagnetic wave causes tilting motions of the spin, as described earlier, which then will radiate the gravitational wave with a wave vector k sub gravitational, which leads towards the right. But now comes the crucial point. Gravitational waves are not blocked by Faraday cages, unlike electromagnetic waves. So the gravitational wave passes right through the left Faraday cage into the right Faraday cage. And in the right Faraday cage, we have placed another pair of levitated Higgs spheres with time-reversed magnetic fields and spins, which then time reversal allows the back transduction of the gravitational wave back into into electromagnetic wave, which leaves through the right through two antennas, again indicated on in orange on the right side of the grounded Faraday cage. So here is a very simple experiment, and remember that the powers we're talking about here are on the order of watts. So it's a very easy experiment. It's not a low signal to noise ratio experiment, so it's going to be very high. So this experiment has never been done as far as we know, but if we do it, then it leads to what I would call, give it a nickname, gravity radio. That is, that we can communicate via gravitational waves in the same way that we communicate with electromagnetic waves or radio waves. And one important feature of this is that the Earth is transparent to gravitational waves, so this opens up the possibility of communicating right through the middle of the Earth, say from California to Australia, and vice versa from Australia back to California. And furthermore, the oceans are also transparent to gravitational waves, and this opens up the possibility of communicating with, say, nuclear submarines that are underneath the ocean. So there are all sorts of applications, both civilian and military, of this kind of device, which we have dubbed gravity radio. With that, I should conclude. Is there another slide, Tim? Yes. Oh, yes. Here are the conclusions of my talk. The first conclusion is that the spin of the electron behaves like a gyroscope. The spin is an inertial guidance object. The spins of two entangled electrons tilt towards and away from each other periodically with time, like two compass needles, as a gravitational wave passes over them. The periodic motions of the two spins lead to periodic motions of their magnetic moments, thus generating electromagnetic waves. By reciprocity, that is, by time reversal symmetry, gravitational waves will be generated by electromagnetic waves passing over the two spins. These pairs of entangled electrons that exist in ferromagnetic matter, like Higgs spheres, imply quantum violations of the equivalence principle due to quantum non-locality. And the Avogadro's number, a very large number of electrons in Higgs spheres, leads to watt-level emissions of gravitational wave power for spin resonance, magnetic spin resonance Qs of around 1,000, which is achievable. Therefore, a Hertz-like experiment is feasible. Is there another slide, Tim? Oh, yes, here's the bibliography in case anybody is interested. The first one I mentioned is by Zhang et al. It's a recent PhysRev letter entitled Search for Spin-Dependent Gravitational Interactions at Earth Range. The second is Bornhill et al. The senior author is Michael Tobar in Australia, and they worked on ultra-high cooperativity interactions between magnons and resonant photons in a Higgs sphere. This was published in PhysRev Applied in 2014. And finally, there's a paper I wrote a long time ago in honor of my old teacher, John Wheeler, which is entitled Conceptual Tensions Between Quantum Mechanics and General Relativity. Are there experimental consequences? And I think the answer, as I hope I've demonstrated in this talk, is yes, with this Hertz-like experiment. Okay, with that, I think I'll stop and ask for questions.